Now that we understand what oxidation numbers are, how to assign them, and what it means when they change from the left to the right side of the reaction, whether it's oxidized, again, losing electrons, or whether it's reduced, which means gaining electrons, now what we need to do is actually practice doing this in a chemical reaction and then determining the whole point, which is to determine which one is losing the electrons and which one is gaining electrons in a chemical reaction. So here we have an example of copper making copper chloride. All right, so what we're going to do again is assign our oxidation numbers. So what we have here, copper all by itself is going to have an oxidation number of 0. Chlorine is going to be a -1 because it's more electronegative of the two. Again, it's closer to fluorine right there. So there are two of them. So collectively, the right side of the compound is a -2 because each -1, and there's two of them, so it's -2. So copper in this case must be a +2. So what we want to do now is look at the elements as they change. So copper goes from 0 to a +2. So it's going from a 0 to a +2. 0 to a +2 is going up. If it's going up, it's an increase. That means copper has been oxidized. Oxidized. Okay. Another example here is we have our silver bromide going into silver. So silver would be, well, bromine is a -1. Silver would have to be a +1 to get it back to a 0. Again, remember, you always start with the right side of the compound to assign its oxidation numbers first. Then you go to the left side of the compound. Here is silver all by its lonesome. It would be 0. So silver is going from a +2 down to a 0. So a +2 down to a 0. +2 to a 0 is going down. That means silver is being reduced. Now, again, what that literally means, oxidized, if it's copper is being oxidized, it is gaining. Sorry, no, it is losing. Wow, that's terrible. And then if silver is being reduced in this example, it is gaining electrons, okay? All right, let's try this in an actual chemical reaction. So what we have is I'm going to go ahead and assign all the oxidation numbers first. Then we'll look at zinc to zinc, copper to copper, and chlorine to chlorine. So zinc by itself is an oxidation number of 0. Over here, chlorine is going to be a -1 like it always is. There are two of them. So again, just like previously on the example above, the one copper would have to be a +2 to cancel it out. Here is a -1 for chlorine. There are two of them. So zinc would also have to be a +2 to cancel out the two -1 chlorines. Now we have copper all by itself, so that's going to be a 0. So I'm going to go ahead now and look at each individual element by itself. So zinc to zinc. Zinc to zinc is going from 0 to a +2. 0 to a +2 is going up. Therefore, our zinc is being oxidized. 0 to a +2 is going up. Oxidation, it is losing electrons. Next, I'm going to look at copper to copper. Copper is going from a +2 down to a 0. +2 down to a 0 means that it's going to be reduced. Okay, +2 to 0 is being reduced. What that means is the zinc ultimately is giving its electrons to the copper. Zinc will be oxidized, copper will be reduced. Zinc is giving the electrons to the copper. Well, let's go ahead and look at the chlorine. The chlorine is going from a -1 to a -1. What that means is the chlorine is a spectator ion. Chlorine is not doing anything. It's just there along for the ride. It is not gaining electrons. It is not losing electrons. It is just present. Much like a spectator at a sporting event, they are not involved in the competition. They're just there to watch. Chlorine, in this case, is a spectator ion. It is there just to watch. All right, moving on to the next example. What we have is magnesium plus oxygen making a synthesis reaction to form magnesium oxide. Magnesium by itself, its oxidation number would be 0. Oxygen by itself would be an oxidation number of 0. In magnesium oxide, the oxygen would be a -2. To cancel that out, the magnesium would have to be a +2. All right, now that we have the oxidation numbers, magnesium to magnesium, 0 to +2, that is going in upwards direction. Therefore, magnesium is going to be oxidized. Oxygen is going from a 0 to a -2 going down. It must be reduced. Again, what that means is the magnesium is giving its electrons away to the oxygen, excuse me. Notice there is no third element, therefore we do not have a spectator ion at all present for the second reaction. The third reaction, we have a decomposition of water into oxygen and hydrogen gases. Water would have a -2 for the oxygen. The hydrogen, to get it back to a 0, would have to be a +1. No surprise there. Oxygen by itself is 0. Hydrogen by itself is 0. So then let's look at hydrogen to hydrogen. Hydrogen to hydrogen is going from a +1 to a 0. That is going downward, +1 to 0. So the hydrogen is being reduced. Then our oxygen is going from a -2 up to a 0. -2 up to a 0 is in a positive direction, so it's the one that's being oxidized. So again, that means oxygen is giving its electrons away to hydrogen in order for this chemical reaction to occur. Okay, that again is basically how a oxidation reduction reaction occurs. We're trying to find, we assign the oxidation numbers based on what you've already learned. Then we look at zinc to zinc, copper to copper, chlorine to chlorine, or magnesium to magnesium, oxygen to oxygen. And we compare to see how does it change from the left side to the right side. If that number is going in a downward direction, then it's reduced, meaning it's gaining electrons. If that number from left to right side is going up, that means it's being oxidized. It is now losing its electrons. If something is oxidized, we have to have something that's reduced. If something is reduced, then we have to have something that is oxidized. All right, so that, yeah. So let me go ahead and go on to the next one. Sorry, guys, I was just looking ahead to see if there was another one. And there is. So this is really important, so I need to go over this with you guys real quick. So the fourth example we have is aluminum chloride making or reacting with sodium iodide in a double replacement to make sodium chloride and aluminum iodide. So to assign the oxidation numbers, we have chlorine, which is a -1. Now there's 3 of them. So the aluminum, to get it back to 0, would have to have an oxidation number of +3. Because again, that would have a net charge or some charge of 0. Iodine is going to be a -1. To get it back to 0, sodium would have to be a +1. Chlorine's a -1. To get it back to 0, sodium would have to be a +1. Iodine is a -1. There's 3 of them, so the aluminum would have to be a +3 to get that back to 0. All right, now that we have the oxidation numbers assigned, let's look at aluminum. So aluminum's going from a +3 to a +3. Well, that's no change. So it's a spectator. So I'm going to go ahead and add spectator over here. Spectator. So the ion, aluminum, is a spectator. It's not doing squat. All right, let's look at chlorine. Chlorine is going from a -1 to a -1. Interesting. Okay, well, it's not doing anything either. So let's go ahead and add that to our list of spectators. All right, well, let's move on. Sodium to sodium, it's going from a +1 to a +1. Okay, this is getting weird. So that's not doing anything either. So let's add sodium to our spectators. Finally, we have iodine. Surely it's going to be doing something, right? Well, iodine's going from a -1 to a -1. Okay, well, that's weird. That means that iodine also, sorry, this was supposed to be chlorine. I apologize, guys. Probably confused by that. This is chlorine. So aluminum, chlorine, sodium, and iodine all are spectators. None of them are changing. Aluminum is going from a +3 to +3. Chlorine is going from a -1 to -1. Sodium is going from a +1 to +1. And iodine is going from a -1 to -1. That means there is nothing being oxidized, nothing being reduced, which tells us it is not a redox reaction. This is RXN is an abbreviation for reaction. It is not a redox reaction. Now, notice what type of reaction this is. What type of reaction is that? Again, I said it earlier, it is a double replacement. That's important. Anytime you see a double replacement, it is never, ever, ever going to be a redox reaction. All of the other ones are your synthesis, decomposition, single replacement, and combustions are all redox reactions, but double replacements are never a redox. So if you ever are asked to find what is oxidized and reduced in a double replacement, don't even bother because the answer is nothing. Nothing is oxidized, nothing is reduced. The electrons are not transferred. We just take the nonmetals and we swap them. That's it. All right, guys, hopefully that makes all sense to you. Again, that's all about oxidation reduction reactions.